All right, let's do this. We're going to pick up where we left off last time. Last time we introduced the idea of this rate law. All right, the rate law is this equation that describes how the rate of a reaction changes as a function of that reactant concentration. Okay? And we're going to sort of kick it up in difficulty here today, but where we started last time is with a very simple reaction that only has one reactant being converted to product. And our rate law for this reaction was that, again, the rate of the reaction is equal to or dependent on the concentration of that reactant, all right, in such a way that it's equal to some constant K times that concentration raised to some power, okay? Again, this is what we call our rate law. These rate laws are going to be a big focus of these chapters. So they always look something like this, all right? So kind of keep this formula in mind here. Rate equals K times concentration of A raised to some power, okay? We have a special name for K. We called that our rate constant. And we have a special name for that exponent. We call that the order of our reaction, all right? And then we said, all right, we're going to develop this strategy that's going to allow us to calculate our rate law here. All right, and what do we mean by calculate our rate law? Again, we have that same formula, rate equals K times the concentration of A raised to that order. And what we need to do is we need to solve for that rate constant K and the order of this reaction. All right, so these are these two unknowns that we're trying to fill in to give us our rate law for our reaction. Okay, and we said that we can do that by studying this data table here, which is the initial concentration of A in the reaction versus the initial rate. All right, so measuring the rate of the reaction right at the very beginning and then changing the concentration of A, doing it again, changing the concentration of A, doing it again. All right, so from this data set here, we said that we can solve these two unknowns. And part of the problem is that there's two of them, right? Anytime we got two unknowns, we can't just fill in numbers and solve here. We got too many variables. So we had to develop a little bit of a strategy in order to solve for these two missing variables. And that was, we first said we're going to find the order of this reaction. And in order to find the order of our reaction, again, the order being that exponent, we need to take the ratio of two data points. So I'm going to take my rate law and I'm going to stack one on top of the other. Get rid of this real quick. All right, so rate equals K times the concentration of A raised to some power divided by rate 2 equals K times concentration of A raised to some power. And we had this algebraic strategy here because that allowed us to get rid of one of those unknowns, that unknown K, right? So now we're just down to that one variable M, and we can solve for that one. All right, in order to get it down from that exponent, we had to take the natural log of those ratios and then rearrange. All right, we're going to play this same game again so we get some practice here, okay? But in this case here, we're going to sort of keep going with our previous example, where at the end of this, the punchline of this whole thing was that we found that the value of that order of our reaction was 2. All right, so what we're going to do is we're going to take our rate law and this data table, and we're going to update it here. Okay, we already did some work. We found that the value of that order was 2, so we're going to go ahead and update this rate law here. Whoops. Put a 2 here. Okay. So we're not done, right? Because what's the other thing we're looking for in this equation? K. Cool. So, but now if we look, we're down to just one missing variable. If we look at our data table here, I can pick any one of these data points. Data point 1, data point 2, data point 3. I can pick any one of them. I have a concentration of A, that's this term here, and I have a rate. So I have everything that I need to solve for that missing variable K. Right? Cool. So everybody take a second. Try to get me the value of K here. Oh, whoops, my rate. I would color in purple. so to be clear, when we say solve for k, we mean that we want to get k all by itself. So I'm going to move that concentration of A squared over by dividing both sides of this equation by concentration of A squared. So now I have k is equal to the rate divided by that concentration squared. All right, and so I'm just going to pick, you can pick any one of them. I'm going to pick just that first one because I got it colored in here. All right, punch that into my forgetting something very important, which is to square that 0.25, the order of my reaction. All right, punch this into our calculator. 0.3. We probably have an extra sig fig on there. Truthfully, in your homework here, I tell you how many sig figs or decimal places to give me. All right, and so we have the value of our rate constant as 0.3. But we're not quite done yet, all right? We want to think about our units of k here, all right? I'm going to kind of do this as a separate problem. You could keep track of your units up here as well, but I kind of think maybe it's more helpful to think of it as a little bit of a separate issue here. So we're going to make another section for our units of k. Okay, importantly, these are going to depend on the order of our reaction. All right, so it's not like we can just say, oh, these are the units of k, these are always going to be the units of k. It's really going to depend on what we found in that very first step of this process, the order of our reaction. Okay, cool. So what we need to do is we need to take our rate law. All right, starting back out with that rate law, just like we did in this calculation here, that was rate equals k times the concentration of A. And in this case, it was a second order reaction, so we're going to square that concentration of A. All right, so actually I'm going to move this down to make a little room. Step 1, start with rate law. All right, step 2, we're going to plug in the units of what we know in this equation here. All right, so plug in our units. So let's think, which one of these variables do we know our units for? So concentration will be one of them. Concentration will be in units of? Molarity, yep. And what is the other one that we know the units of? The rate as well, right? We always know that our rate is going to be in units of molar per second. So that's what we're going to do. We're going to plug in our units for rate, which is again that molar per second, and concentration, which was molar. All right, so I'm going to say, all right, my rate over here is molar per second. We're going to leave k as this variable because this is what we don't know, and this is what we're going to solve for. All right, times that concentration in molarity, but very importantly, just like that number inside that concentration gets hit with that square, so do those units of molarity. All right, so I'm going to square these units as well. All right, and step 3, we're simply going to solve for k. All right, so basically we're going to treat these units as like these symbolic variables and just do some algebra and rearrange in order to get our units for k. Okay, so this is the same thing. I can bring that 2 inside, km squared, divide both sides by m squared. All right, and so I get k equals m over s times 1 over m squared. How can we simplify this? Yeah, so we got 1m on the top And importantly, whenever you see that square, I think it's kind of subtle but really important to remember that that square means m times m, right? I mean, that's what it means to square something, is to multiply it by itself. So one of these m's will cancel out with one of those m's, and I'll be left with 1 over Sm, all right? Per second per molar. Now, our value that we solved here for that 0.03 is going to be that 0.03 per second per molar, okay? And just to be clear, kind of to show, we could have been good and kept track of our units throughout, and we would have gotten the same answer, all right? But when in doubt, you can always just treat your units like an algebra problem and solve for that unknown. Cool. All right. So we're going to kind of just play this same game again, but we're going to up the difficulty a little bit. All right. What we're going to do is take a look now at a reaction that involves not just one, but two reactants, right? There are reactions that have just single reactants, decomposition reactions. A vast majority of reactions take place when two things react with one another. Okay? So step one, we need to build that rate law again. All right, we got a lot of things with the word rate in the name in this chapter. So keeping track of rate constants and rate laws and reaction rates and all that stuff can be a little tricky. Again, these rate law equations are going to be really important. So whenever I say rate law, you want to have that come to mind. All right, that's our goal here for this chapter. So our rate law is, again, this rate equals K, our rate constant, times the concentration of A raised to some power. Does this look familiar so far, right? This is our rate law from the other one. So now we got one extra difference here, which is that now we have this second reactant B. So all we're going to do is tack on to this times the concentration of B. And just like our concentration of A, in our rate law, that's going to be raised to some power. All right? So now that we have these two reactants, now we have this new rate law to reflect those two reactants there, right? So this will tell us how the rate of our reaction depends on the concentration of both reactant A and reactant B. All right? Just like before, right? So an important thing to remember about this is I don't know what these orders are or what this rate constant is just by looking at this balanced chemical equation. Unfortunately, the balanced chemical equation by itself is not enough information for you to figure out your rate law. That's why we had to do that pain in the butt procedure of looking at the data. And that's exactly what we're going to do here again, all right? So let's grab this data set here. Okay. I'm going to give you guys a few seconds to copy this down here. These are the numbers that we're going to be using to solve our rate law for this reaction. All right, so also some terminology that's going to be important here. In this rate law, M, we call that the order with respect to that reactant A. So the order with respect to A. N would then be the order with respect to B. Okay? And the sum of those two orders m plus n, we call that the overall order of our reaction. Cool. All right. So the name of the game here, similar to before, is we got a few unknowns to solve for in this rate law. All right. We want to figure out what K is. We want to figure out what that order with respect to A is. And now we have this second, or rather third variable here, the order with respect to B. This is what we're trying to solve for. So I can just say. All right, and again, we have this data set. And our very first step here is, again, we're going to have to find the orders of this rate law before we can get the rate constant K. So again, we're going to find, and we're just going to pick one of them. It really doesn't matter which one you pick first. M's the first one in the equation. Let's start there. All right, so we're going to find M, our order with respect to A. All right, and we're going to do so in a very similar way than we did before. Again, we can't just use one data point. We got too many variables. All right, so we're going to take the ratio of two data points. All right, just exactly like we did before. All right, here's the trick though. Before, we could have just picked any data points we wanted and it wouldn't have mattered. Now we have to be strategic about which two data points we pick. All right, I'll show you why that is here in a second when we start doing our math. But what we're going to do is, since we want to find the order with respect to A, we need two data points where the concentration of A is changing, but the concentration of B remains constant. All right, so now we got to be strategic. We're going to pick two data points where A changes and B is constant. All right, so which two data points are we going to pick here? 1 and 2, right? Those are the ones where A is being changed, but B is remaining constant. All right, and we're going to take the ratio of our rate laws here. So again, I guess let me just say, let's be specific. Ratio of the rate law of two data points. All right, so that would be the rate of that first data point, which we know from our rate law is equal to K times the concentration of A at that first data point, raised to that unknown power, times the concentration of B of that first data point, raised to that unknown power. And we're going to divide it by the rate law of our second data point. All right, so first of all, this first little trick that we used, taking not one data point, but two of them and stacking them on top of each other. Why did we do that? What do we get to do now to simplify things? We get to get rid of K. right? Good. We need to get down to just one variable here. So by stacking these on top of one another, we get to get rid of k, right? And that was exactly our strategy before, right? We do this to get rid of k. All right, but like we said, we had this added little bit here where we then were strategic about the data points that we chose. So why did we do that one? Well, let's just plug in here our values for b, 1.5, or rather 1.15 and 1.15. Exactly, all right? So, and not only just get rid of b, okay? If I'm going to take this and fill in those values, 1.15 to the n, 1.15 to the n. So yes, I can get rid of b, but not only can I get rid of b, what else can I get rid of? N, right? And that's the big deal here, is that I get to get down to just that one unknown variable, m. So absolutely, by being strategic with our data point picking here, we get rid of n. Okay, and so now what we've simplified to is just that rate ratio equals that concentration ratio to the power of m. Okay, so I want you all to take a second and see if you can't finish this for me here, getting me the order of this reaction. Zoom out so we can see that data table as well. All right, so I gave you guys a little bit of a head start. I'm going to go ahead and kind of quietly fill it in up here. So if you want to check your work or if you get stuck, you can look. All right, so I think one of the trickiest bits here is taking the log of both sides of this equation in order to get that exponent m out of that exponent position. And then we just have the log of our rate ratios, or the natural log. It actually doesn't matter which one you use in this case. I'll just say that we're going to need natural log going forward, so maybe just get in the habit for right now. But it really wouldn't matter in this particular case. But anyways, natural log of the rate ratio divided by the natural log of our concentration ratio. And again, those are going to be pulled from that data table, specifically data points 1 and 2. Cool, so we plug this in here, and what do we get for the order of our reaction with respect to A? 1. Yep, all that work for a 1. Okay? I guess just to be clear, rate of 1, plug in that value. Rate of 2, plug in that value. Concentration of A1, 0.25. Concentration of A2, 0.60. Okay? So we got one of our 3 variables down from our rate law. So let's go back and update things here. All right. This was our goal in our rate law here. I'm just going to copy this. So now we have indeed found one of our missing unknowns here, that that order with respect to A, and we can just plug in a 1 here. All right, since it's a 1, you don't really need to bother to include it, but you can include it. It doesn't really make a big difference. All right, so now we're going to play the same game here. But now I want you all to tell me the order with respect to B. All right, I want to see if you can do this from scratch here. So let's see if we can't find that unknown variable N, our order with respect to that concentration of B. All right, so we got to be strategic about which two data points we pick. Which two data points am I going to pick here? 1 and 3, right? So now I need that concentration of B to be changing, but that concentration of A to remain the same. All right? And after a whole bunch of work, you would have gotten to this similar relationship here. The ratio of the rates of data point 1 and data point 3 divided, or rather the natural log of the ratio of the rates of data point 1 and data point 3 divided by the natural log of the concentrations of A at data point 1 and data point 3 gives you that unknown order n. All right? However, I'm lazy, and I'm going for a speed record here. All right? So let's just look at this data table really carefully here and see if we can't figure out what that order would be. I'm picking these two data points, data point 1 and data point 3. And what do we notice about the rates in both of these experiments? I got the exact same value, right? So what does that tell me here? That tells me that my rate is independent of B, right? No matter what I do to that concentration of B, it's not affecting the rate of that reaction. And if the rate is independent of the concentration of B, the order with respect to B would be 0, right? If I replace this n here with a 0, that whole thing, concentration of B, drops out, right? This just becomes 1. And so my rate law here, if we want to simplify it, is that my rate is simply equal to the concentration, to that rate constant K times the concentration of A. Cool, we got one more variable to go here. Which one? K. Awesome, take a second, tell me what K is. All right, as well as what the units for K should be. All right, I'm just going to rearrange that rate law to solve for K. Now which data point am I going to pick? 1, 2, 3, doesn't matter. Doesn't matter, all right? So they'll all give you about the same value. If you ran through all of them, maybe they would be slightly different depending on, data's not perfect, basically. All right, but nonetheless, we can pick any one of them to get to our value of K, 0.290. I'm going to keep track of my units here in this one line of math. Molar per second. Divided by my concentration of A, that's 0.25 big M. Punch that into my calculator. I get 1.16. We'll be good and mark our sig fig here. All right. And then what will my units be? What's going to happen to that big M? It's going to cancel out. All right. that seconds is still going to be stuck in that denominator position, so my units will just be inverse seconds. Cool. All right, so no, not that one. All right, again, we did sort of the same game here. We had this rate law, but now for this reaction involving two reactants, A and B. So the first thing we did was we built our rate law, rate equals K times the concentration of A raised to some power. But now times the concentration of that second reactant, B, raised to some power. All right? In order to solve for these three unknowns in our rate law, we're going to use this data table here, this data table of initial rate versus concentration of our two reactants. Okay? And step one is to find that order. You can pick any one, actually, but we picked the order with respect to A. All right? And we're going to do this strategy of taking the ratio of two data points. That will allow us to get rid of that rate constant K in our math, which is good because we don't know what it is. All right? But then now the little added bit is that we're going to be strategic about which two data points we pick. We're going to pick two data points where the concentration of A is changing, but the concentration of B is remaining constant. All right? And then we just solve for that value of M. We get that rate ratio over that concentration ratio, rather the log of that rate ratio over the log of the concentration ratio. And then we get our order. And then we're going to play that same game for B. Once we get our orders with respect to both A and B, then we need to find our rate constant K by just picking any data point, right? And then solve for that missing variable. Cool. All right. So again, rate law is going to be very important. We'll see this crop up over and over and over again across the next few weeks. Okay, and so I want to have in our notes here a reminder that our rate law, again, tells us how the rate of the reaction depends on the concentration of our reactant. All right, because this, we really want to make sure we don't get confused with our next topic that we're going to discuss, because they did not do us any favor in how similarly these are named, but are integrated rate laws. All right, and even though these have very similar names, our integrated rate laws is going to give us a very different piece of information. This tells us how our concentration of A, our concentration of reactant, depends on time. Right? Cool. So let's remember that we can get our rate of our reaction. All right? Again, we're going to look at this very simple reaction here where A is going to product. All right? The rate of that reaction, if we remember back to when we were first talking about this stuff, is going to be related to that rate of consumption of A, i.e. the concentration of A, change in the concentration of A over a change in time. And if A is a reactant, and I always need this to be a positive number, I'm going to throw a negative sign in front of it here. All right, but these integrated rate laws, does that first word remind anybody of any class outside of chemistry, maybe in the math department that you would take? Calculus, right? Cool. So now let's take these deltas out of here and instead use fancy calculus speak. This is dA over dt. So if we take this and we integrate it with respect to time, we would get our concentration of A as a function of time. And this is not a calculus class, so great, that's where the name comes from. We're not really going to actually do any calculus here, all right? What's going to happen is I'm going to give you the results, the punchline of these integrations. Okay. Importantly, we are going to use this. You're going to see a lot. This is the concentration of your reactant of A as a function of time. All right, that's all that means. A lot like how in math class you use analogous f of x. Right? Same sort of symbology here. Concentration of A as a function of time. We can just, honestly, you can also just leave out that time portion if it's a little confusing. Okay? So what we're going to do is if we took our our 0th order equation here, right? Rate is equal to K times the concentration of A. All right, but if this is 0th order, I'm going to put that 0 in there. So this just simplifies to K. Okay, we can move that negative sign over. And then if we integrate this, with respect to time, all right, to be honest, y'all are probably better at your calculus at this point than me. It's been quite a while here. But what you would get was negative KT. Remember, when you integrate, you always get plus this constant, right? That's what we have when we integrate, plus C at the end. In this case, these constants have a real meaning here. It's the initial concentration of your reactant. Okay, cool. So fun. That's how we would do this. If you are a big calculus nerd, you can integrate the other ones on your own. But again, what I'm going to do is just give you the punchlines here. So again, this is our formula for the integrated rate law of a 0th order reaction. All right, I'm going to just stack these all next to each other here. So again, these are our integrated rate laws. Oops. if we did the same thing with a first order reaction, or rather a first order rate law, we would get the concentration of A is equal to the concentration of A initially times E to the negative KT. All right, and then lastly, remember we said that 0th, first, and second order are the most common orders for our rate laws. That's not to say that other ones don't exist, but these are the three that we're going to be focused on for these integrated rate laws. Concentration of A is equal to that initial concentration divided by A naught KT plus 1. I'll check my work here. All right. And one of the things that I'm going to do here, just to be consistent with your homework, you're going to be writing these equations. For whatever reason, the system would not let me do something that looks like this. It wouldn't let me have brackets and the little knot here, so we're just going to make this A naught without the brackets. All right, and we're just going to make a note that A naught without the brackets means the initial concentration of A. Okay, so depending on whether we integrate a 0th order rate law, we would get this function. If we integrated a first order rate law, we would get this function. If we integrated a second order rate law, we would get this one. Again, you guys are probably better than me. You could do a third order rate law, et cetera, right? But these are these functions that we get that tell us how the concentration of A depends on the time that that reaction has been going on, right? So we're going to sort of mix two things together and start the clock, and we're going to see how that concentration of A, if A is a reactant, is it going to go up or down? It's going to go down. So these functions tell us how the concentration of A decreases over time. All right, that's sort of our integrated rate laws here. Cool, so let's use one of these integrated rate laws. All right, so I'm going to say that we got a first order reaction here that has a rate constant of 1.16 inverse seconds. All right, we're going to perform this reaction with an initial reactant concentration of 1.6 molar, and we want to know how much remains after 1.5 seconds. All right, so everybody take a second, see if you can't solve this for me using our new integrated rate laws. All right, so step one, first key piece of information here is that this is a first order reaction. And that's important because it tells me which one of these formulas I'm going to grab, right? These are going to depend on the order of your reaction. So for a first order, I'm going to grab that A naught e to the negative KT business. Okay, and then I'm going to fill in here my starting concentration of 1.6 molar times e to the negative 1.16 inverse seconds times that time of 1.5 seconds. All right, I'm going to be good about my units here to make a point. Okay. We can punch this into our calculator. We get the concentration of A has now decreased to 0.281. We're going to leave it with 3 sig figs here. All right, and then what are my units going to be? Yeah, so first of all, sanity check here. Number one, we're solving for a concentration, so let's get units of concentration on the other side, right? But also if we look at our problem, we see that seconds cancel out with this inverse seconds. So the only units that are left are of that initial concentration, that 1.6 molar. And so indeed, my units are in molarity. E is that's a good question. E is a button on your calculator, the bottom line, okay? So yes, that's a great question. Sorry, E is this number. It's kind of like pi, but not quite. It's one of these things that are kind of famous in the math world. But the bottom line is it is a button on your calculator. You have an E usually to the power of, because you're usually using an exponent with it. So yes, if you have not already, take a second and find that button on your calculator, usually located somewhat near the logs, all right? If you got one of these TI-36, it is that button directly below your natural log and log button. Great question. Sorry about that. All right, and then I guess like real quick, just to be clear here, what is E? It's the inverse of the natural log. So the natural log of something to the power, E to the power of something, is that number. All right, kind of how regular log of 10 to the power of something is that number. All right, so it's how we get rid of an E, kind of. In our natural log, rather, is how we get rid of an E, which is going to be important because that's what we're going to do now. All right, so now we're going to do a similar one here. I'm going to ask, we're going to stick with the same first order reaction and our same rate constant. All right, and let's just ask how much time is required for the concentration of reactant to decrease to 1% its initial value. right, so now we're going to take that first order rate law here. All right, and what is it that we're trying to solve for in this particular example? Now we need to get t over here. So in order to get t, we need to have all of our other variables plugged in here, including this concentration of A. All right, so let's just ask ourselves, what would the concentration of A be in this case here? 1% of that initial value, so A naught times 1%, or remember, if we're going to do math, that means 1 over 100. Okay, so to plug that in and using our initial value of 1.6 molar, that would be 0.016 molar. Okay, so then let's take this rate law and plug everything in here. 0.016 molar equals that initial 0.16 molar times e to the negative 1.16 inverse seconds times t. All right, I kind of like to do things symbolically, but we'll keep those numbers in there. Step 1, I'm going to divide by that initial concentration. I get this 0.01. No units. My molars actually canceled out. And then this is e to the negative 1.16 t. All right, and so like we were saying before, how are we going to get rid of that e? We're going to take the natural log of both sides. This becomes the natural log of 0.01 equals negative 1.16 times t. And I'm going to be good with my units. That was inverse seconds. Divide both sides by the value of our rate constant K. So I get T, the natural log of 0.01 divided by negative 1.16 inverse seconds, or about 4 seconds, 3.96997. All right, or we're going to round it to 3 sig figs, 4.00 seconds. So pretty quick reaction here. All right, so since these problems were first order reactions, and they were relating concentration and time, they all revolved around that integrated rate law for a first order reaction. All right, don't worry. I know that was a lot of fun. We're going to do even more algebra with these integrated rate laws. All right, we got one more thing to cover here today, and these are what are called the half-life of a reaction. All right, so a half-life is the time that is required for your reactant concentration to decrease to 1/2 its initial value. And what we're going to learn how to do here is to derive our half-life expressions. Okay, so we're gonna do one together. I'm gonna let you guys do one on your own, and then we'll check your work. And then for today's lab activity, you'll be deriving our third one. All right. So what we're gonna do is we're gonna start with a 0th order reaction. Okay, our half-life expression will be different depending on the order of our reaction. So first of all, let's think about this. Do I want a rate law or an integrated rate law to start with? We need the time required for the reactant concentration to decrease to 1/2 its initial value, which is the one that tells us our relationship to reactant concentration and time. The integrated one. All right, cool. So I'm going to go up here and grab my rate constant, or rather my integrated rate law for a 0th order reaction. Okay, so step 1, start with your rate law. I lied. Your integrated rate law. All right. So just like before, this is actually similar to what we just did before, where we need to solve this for T. But now we need to think about what our concentration of A is going to be here. All right. So we need the time required for the reactant concentration to decrease to 1/2 its initial value. So what should my concentration of A be if it's 1/2 its initial value? A naught over 2. Boom. That is 1/2 its initial value, right? Cool. So what we're going to do is we're going to take our integrated rate law and we're going to plug in A naught over 2 for that concentration of A. That's the bet. All right. Now we're going to rearrange this thing to solve for time. All right. So once we get to this step here, we solve for T. All right. So again, I'm going to give you all a little bit of a head start, and then we'll go through it together. All right, so I'm just going to do this step by step here. So the first thing we would have to do is subtract A naught from both sides. All right, and then we have negative KT equals whatever's on the left-hand side. So what are we going to do? Divide by that negative K. So we get our half-life, T 1/2 equals A naught over 2 minus A naught, all divided by negative K. Okay? Now, truthfully, if you're a little bit of a math nerd, this is a really ugly way to leave this. You can simplify this quite a bit. All right, to A naught over 2K. We can do it. All right, so if we take that minus, we're going to multiply both top and bottom by -1. And that'll allow us to flip this around. Okay. A naught minus A naught over 2. We can take this. Let me get more room here. And this is like everybody's least favorite algebra step here, is factoring that A naught out of both of those terms. Right? So this is the same thing as A naught over 1 minus 1/2. And what's minus 1 minus 1/2? 1/2. So we get A naught times 1/2 times 1 over K. Same thing as A naught over 2K. But look, I don't care. We're not going for style points here. All right? This isn't a math class. I'm not grading you on your algebra ability. All right? I'll put it up here. This is the simplified form, but literally as long as you can get to here, this is exactly equivalent. And this is all you would need to use to find your half-life for that reaction. Okay? So if I asked you for a half-life and you gave me that, that is perfectly fine. All right? I don't need you to simplify it as much as possible here. Okay? What's up?
Will the homework site also accept that?
Yep. Yep, because they are mathematically equivalent. There is no difference between the two of them from a math standpoint. One of them's prettier than the other one, but they're not mathematically different. Okay? Cool. All right, so I want you all to work on the one for a second order reaction. We did it for a 0th order reaction. You're going to do this exact same 3-step process here, just starting with a different integrated rate law. All right, we'll kind of check that out, and then we'll transition into our break. The first one. I mean, it doesn't really matter, but I'm gonna sort of show you here for the first one, so that way you can check your work and make sure you got the process down.
We're using the same values, just second order? Is the only difference?
Correct, because we're not actually using value, right? We never plugged in numbers. All we did was say that the concentration was A naught over 2, right? So that's what the definition of our half-life is. This was first.
Oh, first.
Yeah. The one with the E is our first order.
But the practice question we're doing right now is that second order?
No. So we did the 0th order before, and now we're doing the first order. All right, so here was where we're going to start. And I'm trying to solve this for t. First thing I need to do, divide both sides by a naught. All right, now interestingly, this cancels it out on the right-hand side, which was the whole point of dividing it by the a naught. But what happens on the left-hand side? A naught over 2 divided by a naught. It also cancels out, right? So it turns out that this expression is going to be independent of that initial concentration. It just canceled out from both sides here. So now I'm left with 1/2 is equal to e to the negative kt. All right, again, we had that thing stuck up in that exponent with that magical number e. So we're going to take the natural log of both sides. This becomes the natural log of 1/2 equals the natural log of e to the negative kt. But of course, that gets rid of that e. That just equals negative kt. So I'm going to divide both sides by negative k. Okay, so my half-life expression for this first order reaction is the natural log of 1/2 over negative k. It's pretty much as cleaned up as you can get. You can be clever with your natural log rules and note that this is the same thing as the natural log of 2 over regular k, but it doesn't really matter. Both of those are equivalent, right? So again, what I'm really concerned about is that you can do this process here in order to get your half-life expression. I don't care if you make it as pretty as it can be, all right, as long as you get to the proper algebraic expression. Cool. All right, so I think as everybody can see, Chem1B is a little bit more algebraically intensive than Chem1A. We do a lot of rearranging of equations and stuff like that. It's just one of those things where practice makes perfect, all right? So if you find yourself where algebra is not necessarily your strongest suit, you just want to practice these problems a whole bunch, and then it becomes way more natural about how you move things from one side of the equation to the other, all right? We ran a little over, so we'll